Mathematicians have long searched for reliable ways to translate the chaotic, nonlinear branching of organic tree structures into rigid, sequential geometric paths. This diagram illustrates the mathematical baseline for that translation. A simple full binary tree maps perfectly onto a geometric Dyck path. They share a direct relationship because the permutations of both structures are counted exactly by the Catalan number sequence. But we must abandon the neatness of binary trees to study ordered trees, which allow an arbitrary number of branches per node. To capture this extra branching freedom, the lattice graph must expand into a two-Motzkin path. This geometry adds straight and wavy horizontal steps alongside the standard vertical movements. This creates a translation problem. We need a deterministic algorithm to reliably convert the multidirectional topology of any ordered tree into a strict, linear sequence of two Motzkin steps. Mathematicians Emeric and Louis Shapiro developed the definitive solution to this problem, now known as the phi bijection. The core engine of this translation relies on a strict pre-order traversal, an algorithm that reads the tree's architecture step by step from top to bottom, left to right. This single algorithm acts as a master generator, connecting the geometry of paths to structural rules found in seemingly unrelated mathematical disciplines. By breaking down the mechanics of this single algorithmic translation, we can bridge pure graph theory with the physics of RNA folding and the constraints of algorithmic data sequences. This schematic shows a complex ordered tree and its resulting two-Motzkin path. To execute the bijection, we define the tree's anatomy. First, an internal node is any vertex that is neither the starting root nor a terminal leaf. Dropping down, we find lonely edges, like segments 1, 3, and 10, lines from a node with an out degree of exactly 1. Next are redundant edges. Any downward edge that isn't the leftmost or rightmost child, such as 7, 12, or 16, is classified as redundant. The outer boundaries of those same multi-branching nodes naturally define the left edges and the right edges. Classifying every edge according to this taxonomy provides the deterministic triggers required to generate the geometric path. The algorithm processes the tree using a strict pre-order traversal. It starts at the root but intentionally ignores the very first edge, edge 0, to ensure the final step count mathematically aligns, mapping n edges to n-1 steps. When the traversal hits a left edge, the algorithm plots an up step on the lattice. When it hits a right edge, it plots a down step. Hitting a lonely edge instructs the algorithm to draw a straight level step. And when it encounters a redundant edge, it outputs a wavy level step. Pushing deeper into the tree's hierarchy, the sequence of up and down steps accurately dictates the y-axis elevation of the resulting lattice path. Because every topological feature commands a specific geometric response, the algorithm is perfectly reversible. By reading the steps of the two-Motzkin path, the phi inverse translation flawlessly rebuilds the precise hierarchy of the original tree. We can apply a trivial geometric involution to the space by taking a completed path and simply swapping every wavy step for a straight step, and vice versa.
We then take this mutated path and run the inverse algorithm to see how the tree topology responds. Swapping those horizontal lines forces a topological mutation. Every previously lonely edge expands into a redundant edge, and every redundant edge collapses into a lonely edge. The branching density inverts. Despite this radical reorganization, the total number of leaves on the original tree, added to the leaves on its mutated twin, will always precisely equal the total number of edges plus 1. This algebraic constant guarantees a strict statistical reflection. Across all possible ordered trees with n edges, the total number of terminal leaves is mathematically identical to the total number of internal nodes. By executing a trivial visual symmetry on a line graph, the bijection yields a rigorous proof for a complex statistical equidistribution within graph theory. We can isolate entirely new combinatorial structures by intentionally restricting the inputs we feed into the translation engine. An ordered tree in which no node has an out degree of exactly 1 is called a bush. By definition, a bush contains 0 lonely edges. Because lonely edges map directly to straight geometric steps, feeding a bush into the algorithm guarantees a geometric path completely devoid of straight lines. In combinatorics, these specific, straight-line-free graphs are recognized as standard Motzkin paths, and their permutations are counted by Motzkin numbers. Applying a single topological filter to the tree automatically calibrates the bijection to output the foundational models for Motzkin mathematics. In computational biology, scientists model the folding patterns of RNA secondary structures as non-crossing partitions, preventing physical overlap in the simulated strand. These non-crossing partitions map directly onto Motzkin paths that lack any sharp, immediately returning peaks. We can run this peakless geometric path backward through the phi inverse translation engine to see what topological tree it generates. The algorithm outputs a highly specific variant of a bush, characterized by a strict rule. The left child of any multi-branching node is physically forbidden from being a terminal leaf. The physical constraints governing biochemical folding and the abstract rules of pure graph theory are mapped directly onto one another through this shared algebraic architecture. In algorithm design, Davenport-Schinzel sequences are strings of data defined by a core constraint. They completely forbid any alternating subsequence in the pattern of A, B, A, B. If you take a bush topology and label its nodes sequentially using our pre-order traversal, the resulting string of numbers perfectly satisfies the conditions of a Davenport-Schinzel sequence. The hierarchical nesting required to build the physical branches inherently prevents that AB-AB alternating pattern from ever occurring in the string. By establishing this link, mathematicians proved that the rank and length of these complex algorithmic strings are cleanly governed by Schröder and Motzkin numbers. The Deutsch-Shapiro bijection demonstrates that geometric constraints on a lattice plane, the biochemical limits of RNA folding, and the structural rules of data sequences operate on the exact same mathematical logic. They are translated dialects of a single structural truth.